In this video, I'm going to show you how to create radial patterns using MaxMSP. In this patch and in this visual, I've essentially created a bunch of lines that radiate from the center point with a bit of noise added in to give an offset to each line and create visual interest. So a few basic rules create cool visual elements. Now, I have to admit, this is not my original creation. This is something I've taken from the Instagram page of Kiyoshi Nakauchi, who creates fantastic visual artwork using open frameworks. I have taken the same thing, the same logic, and I've applied it to MaxMSP. I've essentially used the objects jit.bfg, jit.gen, and jit.gl.mesh, plus a fairly simple algorithm to process the incoming coordinates and vertex data. As the end result is really cool, let's see how we can make this happen. This here is my starting point. This visual pattern created by the Instagram account Kiyoshi Nakauchi is what I'm going to analyze and try to interpret or recreate in MaxMSP. I should note that this is created by using open frameworks. And open frameworks is a C++ library or toolkit for creative coding. It's very good for creating these kinds of visual patterns. As you can see, this person has released the code itself, and you will probably realize that this is a text-based programming language, so it is different than MaxMSP. But if you really want to get an insight in how this exactly works, you can try to figure it out using this code. I am, however, going to just look at this image, see what is going on, and immediately try to interpret it in MaxMSP. And I can very quickly make some basic observations. So first of all, this is geometrically very simple, as in there are a lot of lines, there are a bunch of lines. Together they create this sphere or this circle, and there's an offset, so it does not really start from the middle, but it's like there's a tinier circle in the middle, and at the end of these lines, at both ends of each line, there is a little point. So implementing the actual algorithm might be tricky, but I am essentially working with basic geometric primitives such as points and dots and lines and a bunch of connected lines and so on. Meaning I should start by creating my jit.world context. Right, as you know, jit.world is going to create a 3D context for us. We can give this a name, and let's call this, I don't know, radial, because I am probably going to call this video radial patterns. You might know this before me because I have not uploaded this video and I have not given it a title. Anyway, any name is fine, and then we can give it our attributes, floating 1, making sure the visualization, the window, is always on top of our patch, and FSAA1, which is going to enable full scene anti-aliasing, making sure the image, the lines, the dots, the pixels look nice and crisp. Okay, so once I create this, I of course need to press T for toggle because I need to toggle this world on. And I have to consider how I am going to draw these shapes. The most simple, the most easy to use object for drawing a bunch of lines and dots, etc. is jit.gl.mesh. Jit.gl.mesh is going to create GL geometry from matrices, and I just have to give it the name of my JIT world context as the initial argument. So radial, enter, and here we go. An intimidating object for sure, a bunch of inlets, but for now we are just going to need the first one. The first inlet of this object is going to receive a jitter matrix, and it's going to interpret each cell of that matrix as a vertex, so as a point in this 3D space that we are working with. I do need to tell jit.gl.mesh what to do with this information. So does it draw points or lines? Does it connect the lines? Does it create triangles or, rectangle, quad polygons? I need to tell jit.gl.mesh this, and I am going to do this by giving it the attributes draw_mode line_strip. So the incoming vertices, just, connect all of them as if they are a single line. Okay, now let's define our jitter matrix. So jit.matrix, since this is a vertex, so each cell is going to be a vertex, and since we are working with a 3D scene, this matrix should have 3 planes. X, Y, and Z coordinates for each cell are necessary here. Then the data type is float32, and now here's the important part, the dimensions of this matrix. This is important because these dimensions are going to be interpreted as specific things. So let me give it what I want to eventually arrive at, which is 100 by 250, and let me try to explain my reasoning. So a button connected to this jitter matrix, which is then connected to a jit.cellBlock object, is going to visualize the contents of this matrix, which is all zeros, which is okay, which is what we want, which is a default jitter matrix. But here's what I want to do with the dimensions of this matrix. I want each row to be a unique, different line, right? So the vertical height of this jitter matrix is the amount of lines, right? So it's 100 by 250, so there are going to be 250 individual lines in my image. Then I want the length of this jitter matrix, so the horizontal length of this jitter matrix, 100. So each column, each element of each row is going to be a different segment in this line. This is necessary and important because we are going to make sure this line is wiggly. It wiggles around, that there is a certain offset on each point in this line, and there has to be enough points so all the segments look nice and flowing when we actually get to start, making the lines funky and flowy. So 100 by 250, meaning 250 lines, and each line has 100 individual segments. Now we have to put this through our jit.gen blender. So the matrix is going to go into jit.gen, and the result is going to go into the first inlet of jit.gl.mesh, telling the object where these points are and, to draw those using line strip. That is the name of our draw mode. All right, so lock this patch, double click on jit.gen, and here we are in our jit.gen patcher. If I want, I can use the Cartesian coordinate system, right? And this is something I've gone over before in a previous video, but just to sum it up, there are a few different coordinate systems we can use. And Cartesian is, X, Y, Z, axes, etc. This is the one MaxMSP uses. This is the one jit.gl.mesh or any kind of 3D object expects in an OpenGL world. So there are three axes, the X and the Y and the Z axis, and we define a point by giving it coordinates on these three axes, and in theory we can define whatever we want, any kind of point in the space using these coordinates, which is all fine. But if we want to arrive at a circular radial pattern, it might be better to use polar coordinates. Now we can define our pattern in polar coordinates and then convert it into Cartesian coordinates by using pol2car inside our jit.gen patch. And pol2car requires a polar radius and a polar angle. This radius and angle are the two components of polar coordinates, right? So right now we are stepping out of 3D world and we are stepping into a 2D world where we are going to define a point as such. We are going to take a center, right? And let's say this is the middle of the screen. And radius is the distance from that center. So it doesn't matter where exactly I am. The only thing I am looking for in the radius is how far I am from the center point, right? And let's say this is 0 and I can go up to here and this is going to be 1, for example. The second value, angle, is then the rotation of this point in relation to this central space, right? So radius is the distance, angle is the rotation. Angle in jit.gen is going to be in radians, which is a fancy unit, a bunch of pi's and all those cool geometrical numbers. All you have to know is the angles of a circle go from 0 to 2 pi, right? So pi times 2. All right, so what do I want to do then? Well, I want to take the cell coordinates of the incoming jitter matrix, and I want to assign each the appropriate radius and the appropriate angle. So I don't really need in1 right here. In1 is going to give me the actual cell values, which is going to be 0. I do need norm, the normalized coordinates. So these are going to be the normalized coordinates of the input matrix, meaning each cell is going to have a different normalized coordinate, the first one being 0, the final one being 1, and anything in between being anything in between. Since this is a two-dimensional matrix, norm is going to give me two values, or a two-dimensional vector, if you want to express it more fancily, per cell, right? So each cell is going to have two values, and it's going to be that cell's coordinates inside this matrix. Now, for our rows, right, so for line segments, well, I want to start at 0 and I want to arrive at 1, which is very easy. I can just take the x component of this normalized coordinates. Remember, the horizontal cells are going to be segments of each line, and these are going to go from 0 to 1. Just plug it into the first inlet. The polar radius is going to be the normalized x, the normalized horizontal coordinate of each cell. Now, for the polar angle, I'm going to do the same thing. So Swiss y, I'm going to get the vertical component of the cell coordinates. But I don't want this to go from 0 to 1. I want each line to have a different angle that goes from 0 to 2 pi. And this is a cool jit.gen trick. I can create a new object, type in asterisk or multiplication, and then in capital letters 2 pi. In regular Max, this is not going to work. In Gen, this is going to work. So I can multiply my values that are going to go from 0 to 1 with 2 pi, meaning the range of the values are now going to go from 0 to 2 pi. And this goes into the second inlet of Poltecar, and Poltecar is going to spit out the x coordinates, x Cartesian coordinate from the first outlet, and the y Cartesian coordinate from the second outlet. Meaning I can create a vec operator and type in 0 and then 0 and then 0 again to make sure, well, this is a three-dimensional vector. This is the x, y, and z coordinates of my vertex. And I can then take the x coordinate, plug it into the first inlet, the y coordinate goes into the second inlet, and the third one is not necessary. We are not using the z coordinate or the z axis currently in our patch. All right, so let's see how this looks. Okay, so it does create a really cool pattern. I really appreciate it. I don't know if this is going to show up in the video, but I do really like these moire pattern-like patterns that appear once you have enough lines going on. Right, but this is not the final result, of course. The color is wrong. What else? Well, you know, the middle also has all these lines. They actually coalesce into this nice pattern, but let's move this around first by using jit.gl handle. If I connect the outlet of jit.gl handle into the first inlet of jit.gl.mesh, I can actually click and move around this object. And you can see that indeed this is made out of a bunch of lines. And looking at these lines, by the way, I am wondering if my FSAA attribute to JitWorld is correct. I forgot the space here. So if I make sure there's a space between the 1 of floating 1 and the @FSAA of @FSAA, this should look much nicer. Yes, so again, I don't know if this shows up in the actual recording, but this should look a bit crispier, a bit nicer to look at. But in any case, it does create a nice pattern of all these lines. It's like a disk, it creates a nice pattern, but we need a few things. So first of all, we need those dots. Secondly, we need to make sure that these lines don't start from the center point, but they start a bit farther from the center, just like our example. See, here it begins not in the middle, but a bit farther from the middle. That's where the lines begin. Let's start by that one. So going back into jit.gen, the radius right now is decided by, well, the x component, which goes from 0 to 1. And I just have to make sure this starts not from 0, but from some other arbitrary number to give it kind of an offset radius-wise. And I can do this by using the scale object. So let's say I have scale, and then my incoming values are between 0 and 1, and I want to scale these into the range of 0.3 to 1. So it ends at the same place, but it starts a bit later. There we go. Now there is this nice empty circle here. This is kind of looking like a CD actually, especially with those moire patterns appearing on the shape. It is a pretty cool shape. It's a pretty nice 3D design, but we can make it better. And let's make it better by, well, creating those dots at the beginning and the end points of each individual line. There are a few ways of doing this. I am going to simply create more jit.gl meshes. So my initial jit.gl mesh creates the lines, and I'm going to create 2 more jit.gl mesh objects, and each are going to draw a different set of points in my 3D scene. So jit.gl.mesh radial draw underscore mode. This attribute is going to be set to points. And to make sure the points are visible, because these points are really tiny by default, I'm also going to give it the attribute point underscore size. And you cannot see this right now, but I'm typing 3 because that's what I want as the size of my points. See, there it is. Okay, so I need another one of this guy. So 1 for the inner circle, 1 for the outer circle. And then I just need to send the right data into the first inlets of these objects. So why don't I use the same jit.gen patch for this? Here's what I want. So I'm going to essentially steal what I've just done. I'm just going to copy and paste this. Right? And I'm going to copy and paste this again. And I'm going to give these different outlets numbers. So out 1 becomes out 2, and the other one becomes out 3. Now, I want to make it so that these segments do not have different radiuses or radii in my visualization. Because right now, the way I have it, each line segment is scaled to a different value and is set as the radius of the polar coordinates. But I want to not do that. I want to instead tell all of these segments, I don't care where you are, I don't care what you are, here is a fixed value, 0.3. This is going to be your radius. So the angle is going to still be flexible. I'm going to get the full spectrum for the angles, but the distance from the center is going to be fixed for each line. The only thing that is going to be different is the angle. And I'm going to do this twice. So the first one is going to be 0.3, the other one is going to be 1. So I'm going to have 2 different sets here, both come out of different outlets in my jit.gen patch. And as you can see, I have suddenly a bunch of new outlets in jit.gen. Let's plug these in. And I'm also going to connect all of these jit.gl.mesh objects to the same jit.gl handle to make sure I can drag and move all of these objects together as if they are a single 3D shape. Now, if I click this button here, there we go. Okay, why are the inner dots there but the outer ones are not? Because I have done a boo-boo. I connected both of these jit.gl meshes to the same jit.gen outlet. So I gotta do this, click the button again, and there we go. Okay, so the inner circle, you can see the points are still a bit too tiny for my taste, but I think we can leave it like this for now. And again, now this is looking more and more like our bases. We don't have these funky wavy lines yet, but we have the dots, we have the lines, and we are missing the colors though. The background here is black, the lines and the points are supposed to be white. Changing the background color is very easy. I just have to add an additional attribute to jit.world. I have to say @erase underscore color and RGB colors plus an alpha value, so 0, 0, 0, 1. This is going to give me a black background color. To change the color of the object itself, I can use another inlet of jit.gl.mesh. The fourth inlet is going to expect a color array or a color matrix, meaning a jitter matrix where each cell is going to correspond with a vertex, but it's going to be the color of that vertex in RGB or RGBA colors, where each value goes from 0 to 1. Since I want to give everything here a single color, here's how I'm going to do it. I'm going to go back into my jit.gen, and as you can see, it's beginning to get a bit hefty, but no worries. And I'm going to declare another outlet, so out 4. And I'm just going to give this a fixed value. I'm going to create a vector, and I'm going to give it the value of 1 and 1 and 1. So 1, 1, 1. In RGB colors, this is white. So all red, all blue, all green together are going to create white, and this is going to come out of outlet 4. I can connect this to the inlets, the 4 inlets of each jit.gl.mesh object. And upon sending it back, here we go. Now it has a very, very nice, very cool looking white color. Of course, you can create other colors or other color combinations by making use of the norm objects and the angles and radians and the distances from the center points, etc. You can really modify this according to your whim, but right now I'm focused on recreating this. Now is the beginning of the fun part. I want to apply an individual offset to all of these lines in order to create a wavy shape. And to make these wavy, I need to essentially take each segment and I have to change its angle by a semi-random amount, meaning I need to generate semi-random noise, meaning I have to use jit.bfg. Jit.bfg works in a very similar way to jitter matrices, as in I have to declare the amount of planes, the data type, and the dimensions, and for now I'm going to keep it exactly the same as my initial jitter matrix. To visualize the output, I can create jit.p window and connect its outlet there, just like this, and you will see if I send a bang, I'm not going to get anything because I forgot to give a very important attribute to jit.bfg, which is the basis function to use. So which kind of smooth pseudo-random noise do I want to generate? This is controlled by the basis attribute, and noise.simplex is a good one. Noise.simplex. And if I've given it this attribute, as you can see, I get this nice image, but there are some problems. So first of all, this is colorful. I don't want color. I want each cell to have a single value, and that will be interpreted in my jit.gen algorithm as the amount of the offset the segment, the line segment, is going to receive. So instead of 3 planes, I can have a single plane. And there you see immediately that this is now black and white. All of these cells have a value roughly between -1 and +1. So this can be the range of our offset. Now, we need to fine-tune this a bit, but let's implement it already. Let's see how it looks, because I have a feeling this is going to look very funky already. If I go back into my jit.gen patch, if I scroll back up and create in and as an argument 2, now I have a second inlet in my jit.gen patch. This is going to be the entry point for our jit.bfg, for our random noise. And here is what I'm going to do with it. I'm going to take the angle of my line segments, which is Swiss y multiplied by 2pi, and I'm just going to add whatever this offset is to the results. And this should ideally create an offset. Now, this is going to be a gigantic offset, and this is either going to look like crap or it's going to look interesting, but not what we are going for. So plug this into here, bang it to send it into jit.gen, and bang it here. Let's try. There we go. Okay, so we get a very heavily damaged CD or a very strange 2-dimensional donut. This is a very cool shape, so this is already something you can start working with if you're into it, but there are some problems with this. So right now, this image is too large. What I want is to have each line, so each horizontal line in this image, to have a different noise profile so that each contour, each line segment I have in my array of lines in my jit.gen is affected by a different amount of noise, by a different profile of noise. I don't know if it makes sense, but here is what I'm going to do. I'm going to change some attributes of jit.bfg. First of all, the scale. So pack, I want to create a list that starts with scale and then 2 values, 1 for each dimension. If I change these attributes, I still need to send a bang after I play with them. For example, if I make scale 2 and 2, nothing will happen until I click this button right here. And then it's going to change. To avoid me having to click the button, therefore wasting time, what I can do is to use TBL, so trigger bang list. Remember, this object goes from right to left, which means when this list goes in, first the list goes into jit.bfg, and afterwards we send a bang to the same object, triggering output. This way you can see what happens when I play around with the scale attributes of jit.bfg. It kind of squishes or extends or stretches out the image, which means I can do things like this. So now it's very much squished, but having something like this will ensure that each horizontal line has a different noise gradient, right? And then I can use the first scale dimension to see how complex or how simple this noise gradient is going to be for that specific line. And I believe if I have this, if I send it here, and if I click this button again, this is going to look better. Well, now this looks like a very scratched CD or a buzzsaw, and that is because the offset is incredibly great for each line segment. So these line segments are going all over the place in our imaginary CD. So I have to make sure the offset does not affect the lines by too much. Going back into jit.gen, I can try to achieve this by declaring an amplification parameter, which is a very cool way of saying I'm going to multiply this inlet, this incoming value, this offset value, by a value larger or smaller than 1, making the effect more pronounced or less pronounced. So param, and then the name of the parameter, let's just call it amp. Let's be uncreative, and let's give it a default value of 0. And then when in2, so my offset comes in, I can first multiply it by this parameter. Multiply it by this parameter and then add it to whatever the angle of my line segment is. Meaning I can now go out of this jit.gen, click this again, and there, right now the amplitude is 0. The amplification of the line offset is 0, which means we are just getting the regular image, but I can change this parameter outside of jit.gen. I can create a message box saying amp $1. That goes in jit.gen, then a floating number box, and let's see, let's increase it by, I don't know, let's make it 0.5. Click this button again, and okay, it's buzzsawy. How about 0.2? Click it again. It's a bit better. It's getting where we want it to arrive at. And to again avoid me clicking this button all the time, I'm going to use the second outlet of JIT world, which is going to just send a bang each time a frame passes in the rendering world, in my 3D context. So just by doing this, I can change the amp and the result will immediately appear in my screen. And as you can see, with a small amount of amplification, so small amp value, this really resembles our starting point. Look at this, it's pretty much more or less the same. I think a bigger difference is the fact that that one has a higher amount of lines, but that is something we can easily change later. Okay, so an amplitude value of 0.03 seems to create the desired effect. Which is cool, but how do I move this? How do I give it animation like how it is in this visual? Well, I can change another attribute of my random noise, which is offset. So pack, offset, and again, this noise is two-dimensional, so 0, 0. This can go into the same TBL, the same trigger object as before, and again, these floating boxes go into the second and third inlets. Now, what is going to happen when I change these values? As you can see here, and also in the visualization, it kind of scrolls through this pseudo-random noise. So if the X offset gets higher, it's kind of like the lines are being drawn in or it's being sucked inside, just like this. And if it goes into negatives or if I'm decreasing the offset, the noise is scrolling to the right and the lines are coming out of the center point, which is what is happening in this visual lighting. Yep, the lines are going out of the center point and then they go all the way to the end. So we just have to automate this process, and a very simple and a very useful object for this is jit.time. Jit.time, when there is a JIT world enabled in the patch, is going to give out the elapsed time in seconds. So this is just going to increment by 1 per second, and I can just plug this into my offset. And as you can see, this image is being sucked in, which is the opposite of what I want. So I can use the speed attribute of jit.time. So speed, let's say minus 0.5, and now it's going to start counting backwards. Instead of counting forward, it's going to start counting backwards at a reduced speed. Let's give it even less speed, minus 0.25. And there, now it's very, very slow, but still noticeable, and it is radiating from inside to outside, with each line having a different funky shape. Now, this is not over because there is still a tiny difference that, I think is the difference of quality between what I have right now and what this person has made on Instagram. Now, if you're noticing, I don't know if you're noticing this. If you're noticing this, well, first of all, kudos, because this is a tiny detail. But notice that each line begins and ends at the same location, meaning that each line starts from a dot, a point, and it arrives at a point, right? Each dot is connected to a point. This is not the case with our image. All the lines, all segments of lines have offsets applied to them. So their starting points do not coincide with the points that I have created, and their endpoint is also not the points that I have created. And why is this? Because all of these line segments have different offsets attached to them. So this is what we have to change in order to make sure this visual effects, this visual that we are creating is top-notch quality. And what I'm going to do is essentially apply an envelope onto this image. So I'm going to take the output of this jit.bfg, I'm going to create a new jit.gen, and I'm going to apply some kind of envelope function. What do I mean by this? Here's what I mean. In this list of random noise, I want to make sure that the horizontal beginning of each line is always 0. And then it fades into the noise. And once we get to the end, it fades out to 0 as well. Since these values are going to be interpreted as offsets in my actual 3D jit.gen algorithm, starting and ending with 0 is going to mean that the beginning and the ending of these line segments are going to have 0 offset applied to them, meaning that they will coincide with these points right here. Okay, here's how we are going to do this. Now, in 1, out 1. If I send in 1 to out 1, we are going to get the noise as you can see it here in 2D form and in 3D line offsetting form. I want to create a mix between 0 and whatever the actual noise value is. Mix is an object in jit.gen that can mix between two values. The first inlet is if the interpolation is 0, the second inlet is what happens if the interpolation is 1, and the third inlet is the actual interpolation factor. So if my interpolation is 0, it's going to be whatever the first inlet is. If it's higher than 0, it's going to be a mix between these two inlets. And if my interpolation is 1, it's going to be whatever the second inlet is. So let's do it like this. If the interpolation is 0, give me 0, just nothing. And if my interpolation is 1, well, give me in 1, give me the actual inlet. And then I can use the third inlet as the interpolation factor as I have said. So if I give it, for example, 0.5, well, it's going to be a perfect mix between the two. For 0.1, then the noise is very subtle. You can also see it here. Now we are kind of amplifying the noise. But we don't have to do this uniform, meaning that I can grab the normalized coordinates of the matrix. You'll remember what this is from the beginning of this tutorial. And I can single out the x component of these normalized coordinates, which go from 0 to 1. And if I make this the interpolation factor, now look at this, we are starting from 0 and kind of fades into the noise and goes all the way like that up until the 1 point. This is a very slow gradual curve, something we are going to fix, and this only addresses the half of the problem. Now our starting points are aligned with the dots, but the endpoints, if I can zoom out correctly, the endpoints are still missing the mark. So here's my trick for this. I'm going to use fold, which is going to fold a range of values if the incoming value is above or below one of my arguments. And as arguments, I'm going to give it 0 and 0.5, so 0 and 0.5. Meaning if the incoming value is higher than 0.5, it's going to fold. So if I go from 0.5 to 1 in the incoming values, the output will be 0.5 to 0. It's going to fold or mirror. Now doing this with our normalized coordinates is going to make it fold. So we're going from 0 to 0.5 and then back to 0. And again, this works. In fact, this makes the image look much more like an iris than the actual image that we are trying to emulate. but this can be the starting point. So we just need to make sure these curves are a bit less pronounced. So let's scale this first. Or incoming values, so scale, or incoming values are between 0 and 0.5. And I want these values to go between 0 and 1. There we go. Okay, so now we are really going from 0 to 1 back to 0. The same problem persists, that this transition from 0 to 1 is too gradual, but this is where the secret hidden fifth argument of scale comes in, which is going to be an exponential curve. And I don't feel like explaining what exponential curves exactly are right now, but essentially, if it's 1, it's the exact same thing. If it's higher than 1, then the transition from 0 to 1 is going to be much more steep. You can see this 3 or 5 or 10. As you can see, if it's 10, if the exponential curve is 10, it's 0 until the middle point, and then it's really a steep rise from 0 to 1, and then the same thing going back to 0. Again, this might be something to play with. It does look cool in the resulting image, but here is the thing. If you go below 1, it does the opposite. It makes it go from 0 to the non-zero range in very quick steps, in a very small amount of steps. So maybe if I give it 0.5 or maybe 0.25, I'm going to get something like my starting image, my example from the beginning. As you can see now, the starting points always coincide with these points, and then they go out, they get funky, they get wavy, and then they finally arrive at the endpoints, which looks like, let me see if I can make it appear on the screen. As you can see, this and the ending points also coincide with the dots, with the tiny points I have drawn on the screen. Which means that I think I can make a nice comparison here and say that this does look pretty cool and very similar to what we have begun with. Right, so this, let's make it look like a nice comparison picture. Here's what we have made, and here is our starting points. Again, I think the main difference is the speed of the lines evolving. Probably the amplitude of the noise distortion or the line distortion is a bit higher here. And it seems like there are more lines, and let's fix that immediately. So what was it? 100 to 250, meaning instead of 250 lines, let's have 300 lines. Let's make sure our noise matches with this as well. So crit, bang it, give it the same amplitude. What's the problem here? Ah, there we go. If I refresh the jit.bfg, I have to refresh the scale as well. So I can do it like this, lower the amplitude. There we go. All right, and here it is. We have recreated the same image that we have begun with, the same visual we have started with in Max MSP, just by using simple objects and a bit of creative thinking in terms of polar coordinates, lines, line segments, and line offsets. And I feel like this is a great beginning point for a lot of cool applications, such as colors, such as, other noise functions, such as other shapes instead of lines and dots. And you can plug in a lot of different parameters into these algorithms, see what comes up. In any case, I'm sure you're going to have a great time with this. I hope you get really creative with this. I hope you have a lot of fun with this, and thank you for watching.